Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to do our second practice problem on reaction mechanisms. And this problem is going to be the hard type, where it's slow step being second. So let's set up this problem. We have this overall balanced chemical equation, and it has an observed rate law that's equal to NO to the second power and BR to the first power. Now, if you've been in our video series doing these problems, you know in order to have a valid reaction mechanism, it has to pass two tests. It has to pass the stoichiometry test, and it has to pass the kinetics test. So let's get right into this problem and see if this proposal number one, is going to be a valid reaction mechanism or not. Okay, so let's see if it passes the stoichiometry test first. So in order to pass the stoichiometry test, we have to add both these chemical reactions together and see if it equals the overall balanced chemical equation. So when I add these things together, I put all the reactants on the left-hand side. So NO and Br2, NOBr2, and NO. And does that yield the products? So I put all the products on the other side. And let's see if this checks out. Remember, we got to cancel like things. So this is going to cancel out, and this is going to cancel out. Here's my two NOs. So two NOs. Here's the Br2, and that yields two NOBr. Okay, so based on stoichiometry, does that match the overall balanced chemical equation? And when I compare the two, it looks indeed that it passes the stoichiometry test. Now let's see if it passes the kinetics test, which means the rate law of the rate determining step must equal this observed rate law that I discovered through experimental data. Okay, so I'm going to go to my slow step, which is going to be the RDS. And remember, the RDS stands for the rate determining step, because it's the slow step that decides the overall kinetics of the reaction. Okay, that's where the bottleneck occurs. And because this is an elementary step, I can simply write the rate law. The rate is equal to K times each of these reactants. So NOBr2 and the NO. And at first glance, you might say, hey, this does not match the observed rate law, but there's an issue here. And that issue is that I have an intermediate. Okay, remember, an intermediate is something that's produced in one step and then consumed in another step. Okay, and intermediates are not allowed to be part of the rate law. So when you have a slow step that's second, okay, there's a little bit of extra work that you need to do. Okay, the first thing that you need to do is put this equation in equilibrium, saying that the forward reaction is just as fast as the reverse reaction if this first step is fast and the second step is slow. So anything above the slow step is going to be considered to be in equilibrium. Okay, and what you're going to do is you're going to write the rate laws going forward and backwards and setting them equal to each other. Okay, so the rate law going forward, okay, if I said that this is the forward reaction, would be equal to K times NO and Br2. K times NO and Br2. And then we do the reverse reaction. So here's the reverse reaction. That's going to be equal to K and the reactants in the reverse direction. So if we're going the reverse direction, NOBr2 is a reactant, okay, because the reaction's working backwards. Okay, so it's going to be NOBr2. And we're going to set these equal to each other, okay, the rate law. So if this is just as fast as this, then this term is going to be equal to this term. So K times NO times Br2 is going to be equal to K times NO Br2. The K's are going to cancel out, right, for simplicity reasons, okay? And what we're going to do is we're going to solve for the intermediate. Okay, well, the intermediate's right here, and there's nothing that's connected to it. So we don't have to do any division in this problem. Simply, NOBr2 is equal to NO times Br2. So we're just going to do some substitution in here for the rate law. So this rate law becomes K times the NOBR2, which is equal to NO times BR2, and then times the other NO. And then if we were to simplify this, okay, bring it down here, the rate is going to be equal to K times both of these NOs, so that's going to end up being NO to the second power, BR2. And you're going to see, hey, this matches the observed rate law. So this is considered a valid reaction mechanism, okay? It passes the stoichiometry test. When we add things up, it equals the overall chemical reaction. So it passes the stoichiometry test, okay? And then when we do all this work to figure out the kinetics of the slow step, okay, it matches the observed rate law, so it passes the kinetics test as well. And therefore, we have what we consider a valid reaction mechanism. But I do just want to take a second and come back and review that process again, okay? When you have the rate determining step being the slow step second, okay, you write the rate law and observe that there's an intermediate, okay? You then have to put the first reaction in equilibrium and write the forward reaction and the reverse reaction's rate laws. Set those rates to be equal to each other and solve for your intermediate. And after you solve for your intermediate, you substitute it back in and then simplify it and see if it matches your observed rate law, okay? So that's how we took care of that one. Now, I want to do a second proposal. We'll call this proposal number 2, and it's a single step. There's only one step, and it's equal to NO plus NO plus BR2 yields 2 NOBR. Okay, so I kind of want to separate these guys, so kind of have that separated and see if proposal number 2 is valid or not. Okay, well, does it match the stoichiometry of the overall chemical reaction? It does, so it passes the stoichiometry test because basically NO and NO is 2NO, right? Br2, 2NOBr, okay, everything matches up, okay? Now, if it's a single step, this is also going to be the rate determining step. So its kinetics is just K times the reactants. And NO times NO is going to be NO to the second power times Br2. And if you see here, it too also matches the observed rate law, so it passes the kinetics test. So this reaction mechanism is valid as well. They're both valid reaction mechanisms. And for what we're trying to accomplish here is just to see if they're valid or not. Now, I could ask this extra question. Which one is more likely to occur? Proposal 1 or the simple proposal number 2? And what you need to look at is the things that we talked at the beginning of this unit, and that is the molecularity of each of these reaction mechanisms. What does molecularity mean? It means how many molecules are involved in the collisions, okay? In proposal number 1, there are 2 molecules that are colliding, so we'd call that bimolecular. In step 2, it's 2 things that are colliding to each other, so that's bimolecular as well. And bimolecular and unimolecular, when there's just one molecule, are very common types of collisions that occur in chemistry. This last one, this proposal number 2, though, it has 3 molecules. And to have 3 molecules colliding at the same exact time is actually very, very rare. And we call this termolecular, okay? Meaning that there's 3 molecules that are coming together at the same time. So although this is valid, okay, it is unlikely to occur because the molecularity here is termolecular, and up here in proposal number 1, everything is bimolecular, and bimolecular reaction mechanisms, or collisions, I should say, are very, very common. So I would probably say that proposal number 1 is more likely than proposal number 2, but they are both both are valid reaction mechanisms because they pass the stoichiometry test and the kinetics test. If you found this content helpful, please give it a like and subscribe. When you add that comment, it does push out the information to other students that are interested in learning chemistry.